All right. Hi, everyone, and welcome to the Avid CNC live stream, Friday live stream. I'm Sami, and joined by Cory today. Thanks so much, everyone, for being here. Let us know where you're tuning in from, and if you're working on any cool projects this weekend in the shop.
Yeah, thanks everyone for joining. Happy Friday. Should be a really good conversation today about both plywood and plastic toolpath strategies. So really kind of looking forward to digging into some of the different techniques I like to leverage, and I definitely want to hear about some techniques that you guys have. So please drop any questions or suggestions in the chat here and we'll address them.
Yeah, and so we're also hoping to make this kind of series. We have another talk about brass and aluminum strategies as well, and we'll eventually keep working in all the different materials in there and really, going into foam. So foam or other materials that you might be interested in. Let us know if there's a specific material that you want to learn more about, and we'll be sure to get some content on that. So we have actually given this talk before for Vectric user group, which was an amazing event that was a worldwide online free event on Vectric's website and on their channel. So we have linked below to Vectric's channel, and you can go back and rewatch, I don't know, maybe 24 excellent talks by some experts in the field. So, so awesome, everyone. Oh, the Hungry Hiker, awesome. Really great video on the rim to rim to rim talk.
Yeah,
Walk, hike. That's a hike.
it's a hike.
Awesome, Maxie, Tommy, awesome. Thanks everyone for joining, Rodney. And we're gonna get to this talk, and Cory and I will be back at the end to answer your CAD, CAM, chip load, all those kinds of questions. So please queue up those questions for us here in the chat, and we'll be typing in the chat as well. So without further ado, we're going to pass Sami and Cory.
Yes.
Okay, here we go.
Well, thank you, future Sami and Cory, or is it past? Or I think it's future.
Where are we in time? In the space-time continuum.
Quite
sure. All right, well, let's go ahead and jump into some of these topics related to toolpath strategies and CAM. So we're going to talk all about CAM and the different variables to consider when you are setting up your toolpath and really wanting to refine the quality and efficiency of your toolpaths in relation to plastic and plywood specifically. So we're going to talk about our materials, our vectors, the tooling, and then other flexible variables that you'll change to adapt and accommodate the more fixed or semi-fixed variables. So let's go ahead and first start out with talking about material specifically. So for plywood in particular, we have to consider a couple of different characteristics of that material. So the hardness of plywood specifically is very variable in itself, right? So you have construction grade plywood to Baltic birch to custom plywood such as apple ply. So you have,
or hollow core door ply.
Exactly, hollow core doors. Can't forget about that. So you have a lot of variable in consideration with the hardness of the material, and that's going to affect your other selections. So there's also a tear out potential with the veneer to consider when you're selecting tooling, for example. We do have a great variety of work holding options. My personal favorite is the Omer nail gun. I use this almost every time I set up the machine, especially when I'm working with plywood. It's my favorite fast, easy solution, and it's very trustworthy. But when you're considering how your work holding is going to affect your toolpaths, we have to consider the stiffness of the work holding, how reliable it is, if it's going to allow any flex in the material as we're cutting. And then the last thing I would say is the router bit selection is going to be very specific in relation to the type of material qualities you're doing. So we'll get into tooling in a second, but here we go.
Yeah, and the second material we're going to be talking about today specifically is plastics. And so plastics also have very unique characteristics compared to other materials. This includes just the consistency of them, their hardness. There's a wide range of plastics that can be rather soft or very stiff. And we're also going to talk about, work holding with plastics, and then, what are some things that plastics give us trouble with, and heat dissipation and chip evacuation are two things that I know are very important to pay attention to when you're machining plastics.
Right. Plastics are a very, different type of material from plywood, but they're both very approachable materials to work with.
Yeah. And what we're wanting to talk about today here is we have these different materials, and what can we observe about those materials so we can set up the best cam possible.
Exactly. And so after we have our material selected, the next thing I like to consider is the tooling. So there's a lot of different qualities about different router bits that you can reach for. And I'm just going to focus on the four most common that you might have in your arsenal or in your router bit drawer like I do. And the things you're going to think about first is your diameter. So is there a probability of deflection or chatter there depending on the diameter of your tool? What is the flute count, and does this affect your RPM range or your feed rate possibilities, your achievable feed rates? And then the flute type. So this is definitely going to be very important in regards to the material selection that you have. So we have a spiral bit, which has different geometries to consider, your up, your down, and compression bit. And then you also have your straight bit, which is a great neutral and more cost-effective choice. But when we focus on the spiral bits, we have upcut, which is really great for acrylics because it's kind of shaped similar to a drill bit where the chips are designed to be lifted up and out. And when we're thinking about plastic, we want to avoid creating lots of heat. So if we use a down spiral bit on plastic specifically, then we're going to be creating a lot of heat and pressing those chips downward and potentially melting the material. So we want to really avoid that. So upcut is definitely something to reach for when you're machining acrylics or plastics. Something to consider there is the thickness of your material. If you have really thin acrylic, you're going to have a lot more flexibility, and the upcut bit will be able to lift the material upward if you don't have proper distribution of work holding. If you have half an inch thick acrylic or something like that, you're definitely not going to have that problem. But do keep in mind that the thickness and the specific type of plastic might affect that as well. So down spiral, I really like to reach for this when I am working with plywood and hardwoods or softwoods, especially for doing pocket machining. So when I want a really nice bottom surface finish, as well as preserving the top veneer of my material. So down spiral is really great for that. I don't tend to reach for this when I'm doing a through cut, however, and that brings us to compression bit. So a compression bit, you have the geometry of the down spiral and the up spiral on the tip to consider. So you want to make sure to plunge your compression bit below the surface of the veneer so the upcut portion does not make contact with the top surface of the veneer. And when we go into our tool paths later, we'll demonstrate on how to change the path steps here. And then you want to consider the shank type, and then also is it a tapered bit? Are we doing a ball nose bit for finishing? And kind of what results is that going to give us depending on other variables we might consider.
Yeah, I like to think about the type of tooling we have available before I create the tool paths. And so I'm going to recognize my material variables and the tooling options I have at hand before I start leveraging CAM to the full capabilities.
Definitely.
Yeah, so the next thing we want to talk about here is vectors and feed rates. And so what I try to focus on when I'm creating tool paths is the chips. I am trying to set the machine up to make perfect chips. And so I always consider my vectors when I'm assigning feed rates. And what I want to do is make sure that I am setting the machine up for achievable feed rates so that my chip load is calculated correctly. And so we've done a talk on this specifically on feeds and speeds. It's called Chip Load is Queen, and we'll link that somewhere. You'll be able to find that, and we'll deep dive into the different vector lengths and feed rates and how you would approach those with our CNC machines.
So there's a couple settings within our toolpaths that we're going to break down, but just for a little bit of background on why we want to make sure that these are the tools and knobs we're going to reach for. We have our pass depth or depth of cut, if you use that term. I love that there's so many different terms that kind of mean the same thing, and you just kind of reach for the vernacular that works for you. Your router bit selection in terms of the diameter and the stiffness is definitely going to affect how deep your pass depth is, and then your router bit geometry. So as I mentioned before, the compression bit will affect what you want your first pass depth to be set to.
Yeah, so this brings us into the next thing we want to talk about here, and this is climb versus conventional. And with these specific materials, sometimes we want one or the other. And so climb cutting, we are engaging the tool and pushing the chip out behind the bit. And with conventional cutting, we're engaging the material with the bit and pushing that chip in front of the tool, or in front of the direction we're moving. When we do a full profile pass, we're doing both climb and conventional simultaneously because we have 100% tool engagement in the material.
Right. So climb and conventional is definitely really relevant in specific types of tool paths. So not as much in a profile cut because you're engaging both sides of the tool, but when you're doing a pocket, for example, this is definitely going to be really important to consider. So step over next is when we're going to be doing a pocket or clearing, if we're going to be doing a 3D engraving or something like that. So I like to think about this like mowing the lawn, and it's the percentage of the diameter, the router bit overlaps its previous toolpath on the X and Y direction. So we really want to think about how to fully utilize the geometry of the tool that we have selected. So router bits are very much designed to cut laterally and not necessarily cut downward. So we definitely want to make sure to engage the side and the spiral edge of our router bit. So typically the smaller the step over, the cleaner that engraving will be, especially if you're using a ball bit to do a 3D engraving. You have to consider the scalloping, that effect that happens with the ball end mill. And, when you're trying to clear off if you're trying to level a slab, for example, you can go for a larger step over because you're going to be able to sand that pretty easily versus a 3D engraving where you want to have a really small step over and really fine detail.
Yeah.
So that also kind of brings us into raster versus offset. And this is an option that I like to consider, especially when you're looking at the vectors and the geometry that you're being limited by. So vectors are a fixed variable because that's really dictating the end goal here. Raster I like to use if it's something rectangular that we're trying to achieve, but if there is some sort of odd shaped geometry that we're trying to conform to, I tend to prefer the offset. If we're leveling a slab, we'll reach for a raster because it's typically a rectangular shape and I can dictate it to go with the grain.
Yeah, but if we're machining plastic and we want to do a climb cut for 100% of that toolpath, we want to reach for offset, which is going to allow for us to dictate climb specifically, where raster cutting, you go back and forth between climb and conventional.
Exactly. So how do we leverage all of these different knobs and really refine them to, hey Tiller, use these in refining our toolpaths? So we'll research these different materials that we're using and reach for these different variables, adjust those variables, and then repeat the whole process. So we're going to go ahead and make sample toolpaths. We'll try out those toolpaths and then alter and tweak those knobs to refine to get a better chip load and a better cut quality, and make sure that we can really achieve production level speeds as well.
Yeah, so all of you are doing the research right now, and that's fantastic. And I want you to take this information, I want you to generate some toolpaths, and I want you to cut and observe, because really it's that observation is the best research you can do. Is, okay, I've got this information and I'm going to give this a try. I'm going to cut something, I'm going to observe my cut quality, and then I'm going to circle back and try to change these knobs a little bit to see if I can increase my efficiencies or the quality of those cuts.
Right, exactly. So let's go ahead and jump into some toolpaths here in VCarve. We're just going to show you VCarve Pro, which is what I use the most often, but this should be really relevant to whatever software that you're using.
Well, let's jump right into making some toolpaths here. And so what we're going to do here is we're going to start with some plywood. The plywood blank we're going to be using for this example is 12 inches by 12 inches, and I have it set at 0.72 inches thick. Now, it's important to always measure your plywood with a good pair of calipers. Plywood is going to vary in thicknesses and densities. For this example, we're going to be zeroing to the top of our material surface and using the lower left-hand corner as the XY datum, but these are really personal preferences, so, do as you normally would do. First shape here, we're going to make a 10 inch by 10 inch square, and this is going to be kind of centered here. And perfect. So we are going to have a goal of making a perfect 10 inch by 10 inch square of plywood here. And let's hop into our profile toolpath. And first thing we're going to do is we're going to be using a compression bit because we're cutting this material all the way through. Now, Sami, I know you typically zero to the base of your material or to your machine bed when you're doing a profile cut, right?
I definitely do. And this is really important when you're doing a profile cut that you know the exact thickness of your material so that your first pass or the pass depth is going to be very precise from knowing the distance from the spoil board to the top surface of your material. But I do prefer to zero to my bed so I don't cut into my spoil board too much. If you're zeroing to the top surface of your material, you might want to add 10 or 20 thou to your cut through, so you make sure to cut through your material and not leave too much of an onion skin, which might be an issue if you have a thinner veneer.
Yeah, so I like to do my through cuts actually in two separate toolpaths, and that's because I want my feeds and speeds to be different based on some variables, because we have essentially two different operations that we're going to be completing here. So our first toolpath is just to get that top veneer cut nice and clean and get the down cut part of our flute of our tool into that veneer. And so the ideal depth for that with our 1/4 inch end mill is 0.3 inches deep. So that's what I currently have set here for the cut depth. And let's look at that tool in those specific settings. So this is my compression top. I also have the compression low, and that's going to be those underlying toolpaths. But this is my top, and it has a spindle speed of 10,000, a feed rate of 100, and this gives us a chip load of 0.005 or 5/1000ths of an inch.
And I will say something really nice about what Cory has done here is he has pre-programmed the same router bit with different settings, and it has these common circumstances and that we're going to be able to reach for whenever we're going to do profile through cuts, which is a very common thing that we'll be doing. So be sure to take your time to go and set up your common tools that you have available in your router bit drawer that you're going to be reaching for, and invest a little bit of time into your tool library setup.
Yeah, and continue developing this. And so part of the feedback loop of observing your cut quality and then making changes is updating these tools and specifically what they're great at for what type of operation. And so this isn't a set it and forget it type of area. This is something where as you develop different practices or different materials, different tooling, these should be being adjusted on a regular basis to be getting the best results. So we have a pass depth of 0.3 and a chip load of 0.005. This is ideal for our first top pass. So let's go ahead and select that. We have our vector selected here, our 10 by 10 square. We are going on the outside of this vector. I do like a climb cut with a compression bit, and we don't need an offset. Now, this is only our first pass, and I typically don't do a separate last pass with plywood. Sami, do you do a separate last pass with plywood?
For plywood, not as often because the layers of the ply tend to hide the step down lines or the pass step lines, where you might see that a lot more when you're using a hardwood or a softwood and you have to clean that up. So plywood, I'm not as concerned about that as an issue, but it is a nice thing to reach for if you prefer.
Yeah, and other types of operations. And with plastics, a separate last pass can be really, really beneficial. So we'll talk about that in a little bit. But we do not need a tab on this particular toolpath, but I do want to add both a ramp and a lead. And that is because end mills are not great drills. They don't go straight down into our material well. They need lateral movement to evacuate the chips. And so we want to make sure that we're giving that tool that lateral movement, because at the end of the day, that's giving us more tool life, which means the tool is more cost effective. And so we're going to have a ramp here. I like a distance somewhere around 3x the tool diameter. It kind of depends on your material blank size, your machine bed. And Sami, what kind of style ramp do you typically pick?
I typically reach for the smooth ramp. I just like kind of that easy ramp down into the tool path, and it's a little bit easier on the tool, I think, and it's not changing directions like you would with the zigzag. I know that does also give it more of a lateral cut, so it's kind of preference there.
Yeah, so if you have a very small area for you to do a ramp, the zigzag might be good for that, because it essentially has more depth and less space. But right now we have a 1-inch border all the way around this, and so a 0.75-inch ramp and lead in isn't going to be a problem. Then I like a circular lead because, again, it puts a little lateral movement on the tool in two axes rather than one. X and Y. So let's go ahead and call this profile top. And let's calculate this. And we'll preview it here. And what we'll see is we have a lead in here. So we're at full cut depth when we engage on our vector. And we are doing this top cut. So our top veneer is in the down cut portion of that tool. And so perfect. So that is our first tool path. Now let's hop right into our second for this profile cut. And so for this second path, what we're going to do is we are actually going to have a start depth that is at 0.3. And because in this example, we're zeroing to the top of our material, I'm going to add about 20 thousandths to our overall depth to make sure we cut all the way through that material. If we were zeroing to the bed, we could just hit Z here, but we are zeroing to the top of our material. So we are going to add 20 thousandths. So 0.3 is our start, and so that means 0.42 would be to the bottom of our material, and 0.44 is going to be 20 thousandths or 0.02 past our material. And we're going to select our different tool here. And so this is our compression low tool. And what you'll see here is we have some different settings. We have a pass depth of 1/8 of an inch. So this is what I would call a typical or a more typical pass depth, which is the radius of the tool. Would you agree, Sami?
This is definitely the starting point I go for wood-based products. It just definitely is a good starting point when you're programming something initially, and then you can back it off or go deeper depending on what you're trying to accomplish.
Yeah, and the other part of this is we know that only the upcut part of our tool is engaging with that material that's down in the slot. And so this is really going to help with chip evacuation as we get deeper and deeper into this slot, because essentially this slot is going to end up being almost 3 times the diameter of our tool. And anything we can do to get the chips out of that slot is going to allow for our tool to operate at a cooler temperature and therefore have a longer life. And so we'll pass depth of 0.125, and then we're going to bump up our feed and speeds here because there's less lateral force being applied to our tool. And so what you'll see here is we've essentially doubled our feeds and speeds, but we have kept our chip load consistent. And this is something I'm always going to focus on from a machining standpoint, is the machine makes chips, and it's our job to ask it to make the best chips, give it the opportunity to make perfect chips. And in this instance, a 0.005 inch tip is what our target is. So let's go ahead and select that. And because we are doing the outside, we don't need a separate last pass, but this is going to be full depth at this point. And so, Sami, why don't you tell us a little about the tabs you like to use when you're machining plywood?
Right, so for tabs in particular for plywood, I tend to go for a 3-dimensional tab with the triangular profile. It's a lot easier to remove these later on. For the size of tab, you have to consider the quality of the plywood that you're using. So if you're using a lower grade plywood, chances are that you might hit a void on that tab and it will be completely useless no matter which direction it's going. So a larger tab will help you navigate that. If it's a Baltic birch or a higher quality plywood, I tend to like a smaller tab and really trust in the strength of that. Plywood is pretty strong because of the cross grain layering, but when you're thinking about the finish of the veneer, when you're cutting all the way through, it's much easier to remove a tab that's going perpendicular to the bottom grain, because the short grain is going against that tab rather than going through the tab where it has the opportunity to tear out on the back of your piece. So for plywood, I would put them perpendicular to your piece. That would be on the left and the right side of your rectangle. So you can see the grain is going this direction, so I would definitely put the tabs perpendicular to that in this circumstance.
Yeah, so Sami's saying when we put them over here on the left and right, the grain is going to kind of cut through the middle of the tab and therefore make it weaker, because we want to look at the bottom layer of the plywood too. That's an important part here, is it's the bottom layer is what's going to kind of dictate where those tabs go in that instance.
You kind of have to balance out how easy it is to remove, how strong you actually need it to be. You know, you don't necessarily need a large bulky tab in order to hold this rectangle in place when you're removing it. You know, it's a little bit of a balance between like a risk analysis and how, you know, easy it is to finish later on.
Yeah. And if you have a lower quality plywood, or you know your plywood has more voids, the solution might not be just to make really big tabs, but just increase the amount of tabs that you use. And so where you normally might use 2, maybe use 5, because essentially you're setting 1 or 2 of those up to fail because of voids, and you're still going to have more than 2 points of contact when you get all the way around. So We are going to add the same ramp and lead to this full depth profile cup. And so this will be profile low. And let's go ahead and calculate this. It tells us here we're going to be going 20 thousandths deeper than our material into our spoil board, and that is as intended. And perfect. Let's go ahead here and preview this toolpath. And what you'll see here is we're going to go round and round. We're going to make this square. We're going to have the toolpaths. I really like 3D toolpaths because of the fluidity of the machine movement too. We don't get those hard stops. It allows for X and Y to continue moving. And yep, we have a perfect little 10 by 10 square here. This is going to be really high cut quality on both the top veneer and the bottom veneer, and it's going to operate in the machine very efficiently, getting that faster feed rate and getting the chip evacuation, keeping that tool cool, and allowing for you to get a better value out of that tool.
Right, and also note that this is a 10 by 10 inch square, so we're able to get up to that set predicted feed rate that we entered for this particular toolpath.
Yeah, if we would have programmed this at 300 or 600 inches per minute, that would be an unachievable feed rate. And we can definitely achieve that 100 or 200 with one of our Pro Series machines. So let's hop into the next type of toolpath, Sami, which is a pocket, or in this instance, we're going to use kind of like a dado as an example. And so if I'm going to be doing a dado, I want to overcut this. And so I'm going to actually have my Y start at negative 0.5. And I'm going to have a width of 0.7, let's do 7.3, so maybe 10 thousandths wider than our material, and an overall height of 13 inches. And this is going to be a good example of a dado cut here for us. And let's go over here into our toolpath area. We'll create a pocket toolpath. I guess, Sami, we could do either a pocket toolpath or a profile toolpath on the inside of the line here. Which would you lean on for a plywood project?
For this kind of circumstance, I usually just go to a pocket, and I just like that it automatically machines inside that space rather than giving me an additional option of outside the line, inside the line. So for this circumstance, I would definitely do a pocket.
Yeah, and if that pocket depth we were trying to target was less than the downcut area of our compression tool, we'd probably lean on a downcut tool to make that pocket. But because this is going to be a 0.375 depth of cut, we can use a compression tool for this pocket. So let's go ahead and change our tool here. Let's get our compression tool for the top loaded in. You can see all those settings are all there for us. We'll go ahead and remove this downcut tool from our list. And then we have offsets and raster, and we can definitely do a raster cut here, and we can do the profile last. And let's go ahead and make sure, and this would be the ideal scenario, would be this type of raster, right, Sami?
Yeah, this is definitely not ideal. You can see how many times the router bit has to change direction. Also, it's not going with the grain, so there's definitely some issues here that we'd like to avoid. But it's good to show that example. And
yeah. So this is what we would not want to do, right? And this is one click away from perfection. So if we go back into this and we just change our raster angle to 90 degrees and we recalculate this dado, now there's a much cleaner toolpath, and that's going to be efficient, and we're going to get to use that downcut part of our tool on our top veneer because our depth of cut is 0.3, and then we're going to be taking that last 0.075 out with the upcut part of our tool. And the over travel allows for us to not have any cleanup on that part, right? So because we're coming outside of our vectors here, we don't have any corner rounding from a vector that was too short that would show the radius of our tool.
This is also really great for chip evacuation.
Yeah, having those open ends gives your chips a place to go. So this is like a full slot dado. What if we had a rabbet on another piece of material that we were wanting to accept here? And so a slot that was a bit narrower. So let's go ahead and change this slot dimension. Instead of 0.73, let's do 0.375. So we're going to be creating a narrower slot. And Sami, what kind of toolpath would you lean in to plywood on this?
I mean, this is also very similar because of the width of it. You could definitely do a profile interior or a pocket as well. I think I'd probably still go for the pocket just for the consistency.
Yeah. So the pocket cut is going to be, similar type of scenario where we can use a compression tool if the depth of cut is deep enough where we can get that down cut part into that top veneer. But the width of your slot could help dictate which tool you look at. So for a slot smaller than this, you might look at a smaller end mill, but I do feel like our 1/4 inch end mill is going to be adequate here. And so we're going to use that same compression bit. I'm going to choose an offset on this because I want to essentially start in the middle of the cut and work my way out to the perimeter. And we're going to do a rabbit dado. And there we go. We have a nice little small slot that's ready for a board that has a rabbit to go right into it.
Perfect.
Yeah. So let's talk about putting holes in plywood, and specifically with the CNC router. A typical drill bit or drill press, you're going to have RPM ranges somewhere between 200 and 1,000. I mean, I know that's a pretty big window, but it's typically going to be on the slower side of things, right, Sammy?
Especially for drill bits, they're definitely going to be on the lower end versus what we have available with routers or spindles.
Yeah, and so when we are using end mills to do drilling operations or to create holes, there are some strategies that I want to show you guys that I use that I feel like are really helpful in getting chip evacuation and really extending that tool life and the cut quality. And so for this example, we're going to use a 1/4 inch hole as our goal. And so I have drawn a 1/4 inch hole here in the middle of our material. Now, you could use a router bit that's specific for drilling holes at that diameter, and those are great if you have those. And I know these are used a lot of times for pinholes, for shelving, and different things. And so if you have those specialty bits, those are going to work great here. But if you don't have those specialty bits, let's talk about how you can create the best scenario for drilling down into almost a 3x your tool or your hole diameter in depth. And I think this is with a profile pass on the inside. So what we're going to do is we're going to use a tool that's smaller than our final hole. And so this is a 1/4 inch hole. So what we're going to do is we're going to go ahead and select an 1/8 inch end mill. And we have a down cut 1/8 inch end mill loaded up here. You can see here an 1/8 inch end mill, we're going to be moving shallower and a little bit slower. And so I have our spindle speed down to its lower part of the range in order to get the best chip load on it. And so we are at a 8,000 RPM, and I've also slowed our plunge rate down a little bit. Again, trying, it's a smaller tool, and so we're going to be a little bit gentler with it.
What I do like about this is that you've selected an 1/8 inch bit for a 1/4 inch hole, so it's still the radius of the hole, so that when it goes around, it's not leaving a cylinder inside that will break off and somehow get jammed between the bit and the wall as it's lifting up and out later on. So it's still essentially accomplishing a pocket, but it will give you that helix effect.
Yeah. And so we're going to machine on the inside left of the vector. We do not want to do a separate last pass or add a tab, but we are going to add a ramp feature to this. And so what we're going to do is we're going to add a ramp, and the circumference is pi times the radius. And so we know the radius is 0.125. And so times pi, we're looking at above 0.375, just a little bit above. And so we're going to change our ramp distance to 0.375. And what this is going to do is this is going to allow for us to have lateral movement as we move down along the inside of that vector path. And you'll also notice here that I've stopped our cut depth at 0.44. So essentially this program is just going to get us down to 0.44. This is just over halfway through our material. And I do this because I want to potentially give us an opportunity to help evacuate those chips because of the down cut tool. So we're using the down cut because we want to preserve that top veneer, but we need to recognize that when we use a down cut, we're encouraging the chips to stay in the cavity we're creating. And by having an opportunity to maybe remove those chips with compressed air, or maybe change to a different tool that pulls them out as we go deeper in the material, that's why I only go about halfway through here on this first one. So let's go ahead and calculate this drill. And what you'll see here, let's see if I can get a nice little angle where you can really see this, is we are encouraging that tool to move laterally as it goes down into our material. And so let's watch this from above here. And you'll see that that tool is moving laterally as it goes down. And we are about halfway through that material. And so again, this is a strategy where we are trying to encourage the chips to get away from the tool. And we want to, have lateral movement as we go into the material. And if we can do those two things, we are dramatically extending our tool life.
Yeah, absolutely.
And so let's just go ahead and do the final drill here, or to full depth. And so we're going to start it at 0.44 because that's where we left off. And then we're going to go to full depth, which would be 0.3. 0.3 would get us down to full depth. And all of the other parameters can stay the same. We want to make sure we check ramp, 0.375, drill 2. We can calculate, it's going to let us know that we're going to go 20 thousandths through our material. We can see here we have that nice helix move down into the material. And if you wanted to switch over to an upcut tool, that would be the ideal scenario. It's going to get those chips up and out. You could also switch over just to your normal compression bit if you had an 1/8 inch compression bit at that changeover at drill 2. Or you could leave your downcut tool in there and just deal with a little bit less of a tool life. So yeah, so there are some specific tips for plywood. Please, if you have questions, put them in the chat, and we're going to do a Q&A here very shortly about plywood, but we're going to switch over to plastics and give you some tips on that.
Awesome. Let's do it. Okay.
All right, well, let's talk about some strategies for plastics in particular. And so let's set up a workpiece here. And so we're going to have some the same general parameters for our workpiece size. We have a 12 inch by 12 inch piece, but we're going to put this at 0.75 inch. And that's because plastics typically come in a very uniform thickness, and 0.75 is a common acrylic thickness,
Yeah,
right,
I really
Sami?
like that. Acrylics and plastics are very predictable in terms of thickness. There's a very tight tolerance there. Do be sure, depending on the thickness of your acrylic, there will be different qualities that surface. For example, if you have a thinner acrylic, there will be a lot more flexibility versus a really thick acrylic like 3/4 inch is going to have a lot more stability and not be so subject to lifting from an upcut bit or something like that.
Yeah, and plastics have different properties. And so what we're going to review here specifically is focusing on some chip evacuation techniques, but test your plastics and find out the ideal chip load for your work holding method and the tooling that you have at hand. So let's first start by cutting that 10 inch by 10 inch square. And let's talk about that a little bit. So we have a 10 inch by 10 inch square, perfect. And what I like to do when I'm cutting deep into material, especially when chip evacuation is really important, I like to create an evacuation path for some of those chips. And so what we can do here with this 10 inch by 10 inch square is we can create an offset that is about the tool radius wider than the original. And so we have 0.125 here as our distance, and it's an outward right offset. And you can see that gives us that additional line outside. And what we're going to do first here is create a clearance toolpath with this line. And so we're going to go over here to our profile toolpath selection, and we're going to have this go halfway through the material. So 0.375. So this is going to go halfway through the material. Let's pop in here and select our tool. So just like with plywood, even though it's the same tool, I have different setups for pockets or profile, downcut, upcut. And so chip evacuation is really important here. And so we're going to choose to use an upcut tool that's going to bring those chips up and out of the material. And because we're having some longer vectors here, I prefer to use a 2-flute tool than a spiral O-flute, just because sometimes the spiral O-flutes tend to grab at your material. So I save those for smaller vectors. And so we have an upcut end mill 1/4 inch, and you can see here our chip load as it's calculated at 80 inches per minute is somewhere right around 4 thousandths of an inch. Plastic chip loads can range from about 3 thousandths all the way up to 15 thousandths. And so there's some differences there based on the thickness of your material and the type of plastic it is. So we'll go ahead and select this, and we will be on the outside right. We're going to do a climb cut. This is a great thing for you to test with your materials as climb or conventional. But really this is a profile cut, so 100% of the tool is going to be engaged. in this clearance pass. And so whether it's climb or conventional in here, really is just telling us, is it going clockwise or counterclockwise around the vector? We don't need a separate last pass in this case, and we don't need tabs, but I do want to add ramping to this. And so let's go ahead and add that. We have smooth ramping, and because we're only ramping to a cut depth of 0.1, we don't need that ramp distance to be too long. So I've shortened that up to 0.375. And we'll call this one clear. And go ahead and calculate and give us a little preview here. And you can see we're starting in the lower left-hand corner, and we're creating this clearance toolpath. And then so to create our final toolpath here for our 10-inch, we're going to go back to this, and we're going to start at 0, but now we're going to go to 0.775. So we're going to go 20 thousandths beyond our material thickness. We're going to use that same 1/4 inch upcut end mill, try to get those chips out of this canyon we're creating. We've got that same chip load. All of those settings are the same. Now, Sami, in this instance, would you use a last pass with acrylic when you were cutting all the way through?
I think in this case I would, because I prefer not to have to do too much sanding, finishing to acrylic in particular, especially if there's a gloss surface that I don't want to accidentally nick with my orbital sander or something like that. And the upcut here, you'll have a lot of room for chip evacuation. So I definitely think including the separate last pass in this circumstance is definitely a bonus.
Yeah, the gotcha there is you got to make sure you have the flute length to do that, right? You need that flute length that's longer than 0.77 inches. So let's go ahead and do a separate last pass, and let's do this at 0.025, so 25 thousandths thick. And so it's going to come back and give us a nice last pass. And then, Sami, what kind of tabs do you like to use with acrylic?
Well, for tabs in particular, I prefer a square tab. And I like to go about an 1/8 inch thick and about 3/8 inch wide. Having the pyramid shape or the 3-dimensional tab, you have a higher risk of tearing out, which I prefer not to. You don't have to worry about grain here, which is really great. So using the upcut, you don't have to worry about tear out on your material. And with your tabs, you don't have to worry about grain strength. So.
Yeah, I try not to put tabs right in my ramping area of the toolpath, because as we get lower down into that material, sometimes it can interfere there, and so I'll just move it over here to this lower corner, and we'll add those tabs. We do want to ramp our tool into the material again, so we'll go with a smooth 0.375 inch ramp, and we'll call this profile 1. And as you can see here, it's giving us that lovely warning that we're going to go into our spoil board, and we know that, and that's okay. And so here, I'll slow the preview speed down a little bit so we can see this. But once we get down to the bottom of our clearance pocket, you'll see that there's going to be some additional room now for those chips to get up and out of that deep canyon. And that's because we've created that additional tool radius outside of the canyon. And chip evacuation with plastics is the biggest tip of the plastics talk, right? It's this, let's get the chips out. And if you're getting stringy chips rather than more traditional chips, a chip breaker tool might be advantageous, or potentially adjusting your depth of cut. HDPE can sometimes get pretty stringy. In this instance, if you notice your material is really stringy, maybe break your toolpaths up into smaller sections, and so you have the opportunity to come in and clean that area before you continue through your entire sheet.
I also like that with that first toolpath, you're creating the chip evacuation channel, but then also on the second pass, you're not engaging so much of the router bit on that finish pass, so it's not working as hard. You're extending that tool life, and you're getting a better quality finish in the end.
Yeah. So cool. So that's a little tip on the profile cut. Let's hop into some pocket cutting and talk about cutting a pocket. So let's do a 0.5 inch little circle here in the center of our work. And we'll go into our pocket toolpath creation here. And let's go down to 0.375. Let's pick a new tool here. And so I like to set up a tool specifically for pockets. And in that tool, I tend to drop my step over down a little bit with plastics. And I'm trying not to create as big of a bite into the material. This really helps with the stringing factor. And so if you're taking a smaller bite with that spiral cut, we're not going to get as the potential for as long as strings. And so we're down here at a 0.003 or 3,000ths chip load. We can probably bump this up a little bit in our feed rate to get the right chip load, but in realistic scenarios, this is a 1-inch movement, and so these feed rates, might not be great. And so this would be an example where that spiral O-flute bit might really be beneficial for the plastic you're using if you're not getting the right chip load. So let's keep this down at 60, and this is an achievable feed rate with our Pro system. And we'll go ahead and apply that and select that tool. And for this in plastic specifically, I really like to use the offsets factor because we can guarantee it's either going to be climb or conventional cut, where a raster is going to go from climb to conventional back and forth, right, Sammy?
And also, since it's a circular shape, the offset is going to be far more efficient and just kind of have a better look in the finish.
Yeah, we do want to ramp this, and we'll do that same 0.375-inch ramp distance. And we don't need a pocket allowance right now, and so let's go ahead and calculate this here. And perfect. So yeah, so we'll see, we're doing this in a couple passes, and perfect. So good chip evacuation, pocketing toolpaths, we have that room around the tool, but let's pretend like we wanted to make this a counter bore for a through hole. And so let's go in and draw that through hole here. And so we'll go in and we'll put a 0.125 at 6.6. Perfect, and there's our through hole. And let's go ahead and use a drilling toolpath. And I really like the drilling toolpath because it's geared towards chip evacuation, right, Sammy?
Definitely. So I love that you can utilize the Peck drilling where it touches down and lifts back up, and then it continues to go down at the set pass depth. But it really gives an opportunity for those chips to come up and out and not create too much heat.
Yeah, so you could use that helical style profile toolpath like we talked about in the plywood. But if we have this upcut tool already loaded in and we want to do this, we can use Peck drilling. And so I do like to retract above the cutting start rather than just from the last previous height. And you can also add some additional gap there if you really want to lift it up. If you're seeing that you are having gumming, or you are seeing the system overheating a little bit, sometimes increasing this gap and decreasing your plunge rate down to maybe a 5 or a 7 plunge rate, you're just going to give more time between the engagement of the material. You're going to allow for your tooling to cool down, the material to cool down a little bit potentially. Dwelling at the bottom is not going to allow for time to cooling, right? You're going to be down there in the heat, and I would not dwell at the bottom if you're dealing with any type of gumming. And you can see here we're starting at a start depth of 0.375 and then a cut depth of 0.395 because this is a counter bore, right? We're starting halfway through the material already. So let's go ahead and it'll tell us, yep, we're going to go through the material 20 thousandths. And drilling toolpaths look nice. It's just a nice green vertical line, and we can see it Peck drills and comes right up there. And so that Peck depth and retract height is something that I feel is determined by your tool. And if you use a single O-flute tool with a drilling operation with plastics, the tool is going to move on you. You are going to get an odd round hole, and that's because there's only one cutting edge. And so in this application, that 2-flute tool would be ideal for drilling in plastics.
And order of operations here, if you're going to do a counter bore anyway, you might as well relieve that area first before doing the Peck drilling operation.
Yeah, and sometimes you can add flair to your counter bores with a shape. This counter bore operation is very similar to our clearance toolpath here, in that we are essentially giving the diameter of our tool some space within the middle of our flute to get those chips up and out of the canyon we're creating, instead of having to travel all the way up the flute of the entire tool.
Yeah, sometimes I do like to make the counter bore like a hex shape so that my hex bolt fits in perfectly.
Yeah. Well, there are some tips about plastic. Please leave some questions in the comments for us. And yeah, thank you so much for joining us here with Plywood and Plastic Toolpaths.
Awesome. Let's go answer some questions to the future. Marty,
Yeah.
let's go. Sorry, that was weird. No one's going to get at my obscure references. Okay.
Oh, it's sequential.
Okay, here we are back live and ready to answer some of your questions. You have some really great questions here, and we have them queued up.
Yeah.
Oh, I forgot to thank past Sami and Cory for doing all of that hard work ahead of time.
Yeah.
Okay, awesome. Let's see, what order should we do this in? I'm just going to hop around and make sure we hit all these good questions. Let's start with Robert Tool, your question. This is a really great question. So are techniques for carbon fiber, like wood or acrylic or aluminum, like the ways you approach your toolpath strategies? I think the thing that would be bringing these all together is how you refine your chip load. Right, and we also have a live stream called Chip Load is Queen, and that's a really great reference to go to because if you're trying to refine the chip load and the chips you're getting, the quality of that will help point you in the right direction of how to tweak those different knobs when you're refining your tool paths.
Yeah, we did discuss this a little bit with Keegan at Dark Arrow also. And one thing to really take the most in consideration with carbon fiber is making sure you're protecting your respiratory system. That material is really harsh on your respiratory system. So make sure you have exceptional dust collection or are wearing the proper PPE when you're cutting it. But yeah, focusing on the chip load and your vectors is going to be a great place to start.
Right. Okay. So let's go up to other questions here. What are your thoughts on GWizard Calculator for it's a software program for zeroing in on feeds and speeds with different materials, and is it worth the cost in your opinion? That's another great question. I've used it a little bit a couple years ago, but it's not something I've relied on as a go-to tool. I know that Vectric recently included a chip load calculator in their toolpaths recently in the recent 10.5 update. So if you have the recent 10.5 update, I would recommend checking out that update because it is a great tool to help you get started, and then you can kind of make adjustments as you need to.
Yeah, and I think there's a lot of great information in the GWizard and Feeds and Speed kind of pre-made calculations for you there. A lot of those are geared towards really high density materials, ferrous and non-ferrous metals specifically, and more high cost tooling. And so traditional milling systems where there's a lot smaller window of chip load and forces you can apply. Generally speaking, using woods and plastics, we have a much larger window. And so your kind of initial guess and then refinement, there's not as much liability there and you breaking your tool or breaking your workpiece free from your work holding just because we have a little bit less dense of material and a little bit less forces being applied to our workpiece.
Right. Okay, so we have a question about boring bits and plunge rates.
Yeah, so I think a plunge rate with our Z-axis, you could probably be somewhere between 10 and 30 inches per minute on your plunge with the boring bit, depending on the diameter. Peck drilling is going to be something you might consider doing that in order to encourage that chip evacuation. If your bore is going deeper than maybe 1 or 2x the diameter of your tool, I'd probably consider a peck drilling operation at that point. And then depending on that peck depth, you could kind of play with a couple different settings between 10 and 30 for your plunge on that boring tool. Now, with a traditional end mill, that plunge rate, if you're doing a ramp, is going to be the ramping speed and the Z-axis speed of that tool. And so with a end mill and ramping, I might consider, something between 30 and 80 IPM as my plunge rate.
Right. Bernie has a question about Countersink and V-Bit. I definitely do this all the time, especially for when I'm plotting out the work holding screw locations for big sheets of plywood. When I want the countersink, the head to sit below, or when I want to even just mark the holes for where my screws will go in a cabinet build or something like that, might be a really great use for that. Bernie, do you have a specific question about countersinks and V-bits? Let me know. And we have a great question here. When you cut aluminum, do you prefer mist or air to clean up the chips? A mist does make a bit of a mess, and on the spoil board, yeah, I can understand that, right? Because of the extrusion, you can kind of make sure that the mist can kind of drain out through the extrusion. I definitely prefer the air cooling with but you also need to worry about the projectiles of your chips as well. So making sure you have the proper PPE for that.
Yeah, and I think really when we talk about air or mist, what the real question is are you getting adequate chip evacuation? And if you're not, then let's change something to try to encourage adequate chip evacuation. Because a mist coolant, we're not trying to cool our tool like flood coolant with just a large mass of a colder liquid. What we're trying to do is lubricate the tool and the canyon or the material that we're cutting in order to encourage chip evacuation. And so I think mist or air should really be kind of dependent on the type of toolpath tooling and vectors you're machining, and do you need additional chip evacuation? And then let's kind of take a couple different approaches to try to encourage that. That could be some of these additional profile toolpaths that we did around the canyons we were cutting like we did here in the plywood, or that could be some other kind of cam tricks that can really encourage chip evacuation for that scenario.
Right, awesome. Let us know if you guys have any more last questions here. Cory, did I miss anything on our list? I don't think so.
Yeah, no, I think we kind of touched base on all those questions. Just, I guess, V-bits in plywood, I guess we could talk about that a little bit, just in a general sense of using a V-bit with a veneer. A V-bit is typically a straight edge, and so we're not going to have kind of that down cut quality to preserve that top veneer. And so with a V-bit, I might have a slightly larger finishing pass, so that if there is any chipping that happens during that initial material removal, we have just that final kind of, not an onion skin, but more of kind of a finishing pass on that top veneer, so we can try to really preserve that by putting less force on that cut that's setting our final edge.
Yeah, and the V-carving oftentimes just leaves that fuzzy edge. So if you have a nylon brush, like a soft nylon brush that's not going to damage the surface, but just kind of clean that up, that can also be very useful. But usually when I'm doing a peck drilling operation for countersink, I don't typically have that problem compared to when I'm doing, an illustration V-carve, really detailed, or a logo design. I might have that problem a little bit more versus just the simple countersink. Well, wonderful. Well, I hope you all can join us next Friday at noon. We are going to be talking with Dave Stanton. If you don't know David Stanton, go check out his YouTube channel. He is the creator of the Stanton Workbench. Really amazing CNC user. He also loves a classic hand plane, which Cory and I love as well. So be sure to come join us. And he is getting up super early because he lives in Australia, so that we could keep our regular noon time. So thanks, Dave, ahead of time for that. And we hope you all can join for that. Let's see. Just looking at this last question here. I have Mach 3 and Fusion 360. Okay, so Fusion 360 and Mach 3 Fusion specific videos. Do we have any? I think we definitely do have some. All of our content is evergreen, and on our YouTube channel, we have switched over primarily to making only Mach 4 content, but we definitely have Fusion and Mach 3 videos. So if you want, you can email us at support@avidcnc.com, and we'll be sure to get you that playlist and get you set up there.
Yeah.
Awesome.
Thanks everyone for joining. Have a great day.
Awesome. Thank you. Bye.